It is very resource intensive, especially the memory, so it gets expensive really fast. So that's actually the reason. Now you can go, or you can go into the details. So this is large language model. As you can see here, it is around 60 billions, 34 billions. This is the winning large language model, right? And to have a comparisons in gigabytes, for example, okay, 60 billions of neural networks, we have 60 billions nodes. What it represents in terms of hardware, 60 billions in floating point. Normally, we will use, I think it's 16 bits of floating point, F16, which is already like really great. But the original one it will be 32 bits, which is if we calculate, then 32 divided by 8, so it is 4 bytes per node. So what that means, if we have the best performing one is 60 billions, but this is MOE, it's a little bit different. But anyway, so let's say 60 billions multiplied by 60. So you would require 240 gigabytes. Yes, because it's billions, which is 10 in the power of 9, which is equivalent to 2 gigabytes. So you'll require 240 gigabytes in order just to run one time for one user. So this is impossible. So that renders the main challenge of AI is actually require a lot of memories, and especially if you want to productionize the large language model to the cloud for more users, for example, then you will require even more than this because this is just one user. And let's say you have 10, then you require 2.4 terabytes in if you want to have the users run at the same time. So, what we normally do about that is, first of all, we try to make the model smaller. That's why, for example, we have this one, which is 3 billions. So there is this, the size of the model and also the accuracy of the model itself. So that's a trade-off, right? As we can see here, this is an amazing benchmark, by the way, OpenLM leaderboard. It just lists all of the neural network based on the accuracy from high to low. And naturally speaking, the bigger the neutral network is actually performing better. This is the thing about transformer base. So we've got now 7 billions, and 7 billions is something that I always aim for because it has the nice trade-off between accuracy and also model size. But you can even go smaller than that, which is like 3 billions, for example, right? So that's one thing, right? And then the second one is actually, oh, okay, now we've got that, then we can actually quantize. I'll explain a little bit about quantize uh, later on, but also I want to show you. So we talked before about the gigabytes required for the RAM. How if um, the actual hardware, what kind of hardware we can buy in order to run it? So for example, if you have a Raspberry Pi, okay, there's like GPU, but probably you want to use the GPU there. Important thing is the RAM. We've got here 8 gigabytes of RAM, right? Just 8 gigabytes, and this is already the upper tier of Raspberry Pi. And 8 gigabytes, you can't even run the largest model. You can probably run the 7 billions one, and it has to be quantized too. I will show you about quantize a bit later. And then, how if you have a GPU? So, NVIDIA T4 is actually the most cheapest GPU you can have on the Google Cloud Platform or this kind of cloud platform. So we've got here 16 gigabytes, right? 16 gigabytes of RAM, which is, by the way, if you're just a consumer grade, you want to use GPU for your gaming, 16 gigabytes is actually pretty a lot. However, for AI, 16 gigabytes doesn't seem to be too much. So 16 gigabytes, you can probably run the 7 bytes or the 34, but it's going to hurt the performance real badly. So probably 7 billions. And do note though, the main difficulty here is we want to scale. So even if you have 7 billions here, you can probably only run like one or two users at the same time. While you want to provide millions of users if you scale up your business. So if you want to actually provide for millions of users, then it becomes more difficult. In comparison, back in the day, or like right now, if you want to serve a website is not too resource intensive. So when you actually provide the websites, you can run like you can provide 100 users in just one CPU. So this is a very big difference, a new kind of challenge that emerged because we have this large language model, which is used by ChatGPT, which is used by the Microsoft right now and everyone in the AI area. The main challenge. The only difference is OpenAI right now is funded by these large corporations, so they have a lot of money. So basically, it means that they can burn money much easier and in a much discounted price because they have this kind of collaboration. So something like this, if you are making a business, this is something to really be taken into consideration. So now, last but not least, because now we are actually also talking about the solution, how to actually optimize this so we can really fit a lot of stuffs within one GPU or just one resource. So this is something called quantize. So given a large language model, we can actually reduce the amount of memory required to run it with probably less accuracy. But this less accuracy sometimes is negligible. So the original one is 32 bits, right? 32 bits converted to bytes is 4 bytes. So if you want to run, for example, this 3 billions, which is, by the way, is already a small large language model. So then we just multiply this 3, right? If 32 is not written here, with 4. So it requires 12. Now we are talking about how about we are using 16 bytes, 16 bits. And to define, maybe for you guys that do not know this, so each of the node will is sort of like a number in the computer. So this number is represented as bytes and bits, right? And this is normally speaking, depending on how you set the numeric system, the number of bits required to represent one node can be different from one to another. And the original one is something we call floating point. So this can provide you a more detailed and the more basically what I'm saying, the more bits you have, then the more accuracy and precision that number would represent, right? Because you can fit more stuffs in this placeholder of numeric system. So if we have like floating point 16, then this is bits, so you can just divide by 8. So this is 2, right? So then you just multiply this 3 with 2, then will be 6 gigabytes, right? So we can go smaller. So this is 8 uh, bits, 6 bits, 5 bits. I normally use this one, so this is the most recommended quantization. And if you want to try also another model, quantize one, so you can search for GGUF. GGUF also allows you to actually deploy in CPU or in GPU. So up to you. But it can also like in CPU. So that's pretty much fine. So this is like a sweet spot. That means each of the user will only require 2 gigabytes. So 2 gigabytes, if you're using Raspberry Pi, you can actually serve around 4 theoretically, but probably can only serve around 3. Okay, so that's one. By the way, like external additional thing, you can also try swapping. So if you can have a swap file, you can increase the RAM from 8, let's say, to 16 or to 32. Then that RAM is actually like a virtual RAM that uses the hard disk drive or the SSD that you have. It's a bit slower, but you can serve more customers like that. All right. So I think that's it. So really the main challenge for this large language model is that it's very resource intensive, especially the number of RAM. CPU wise, of course, it is more resource intensive. It's like running a game basically. However, what we normally really take into account as the main bottleneck is the amount of memory that can fit within the resource that you have, right? If you have GPU, that's perfect, but most of the computer doesn't have that. And even if you actually want to deploy GPUs in cloud, as a picture, 1 month for the T4 GPU, like the lowest cost GPU, will cost you $200. So that's just one, right? And that can only serve probably one or two users. So the resource, especially in memory, is very challenging here. All right. Thank you for watching and stay tuned.